So far we have discussed what happens to light when it is reflected. And as you recall, whenever light is going to meet an interface between two different media, part of that light is going to be reflected. And what we have figured out is that the angle of incidence is equal to the angle of reflection. And an application that is based on that is mirrors that we have finished discussing. Now, as it happens, in addition to reflecting, part of the light is going to move into the medium, or it's going to be transmitted in the medium. The term we usually use is refracted. So we say light is refracted. Now, as light moves into a different medium, the transmitted beam, instead of moving in a straight line, it's going to bend. Most of the time it's going to bend. We'll see one case where it does not bend. Now, it usually bends, and that term bending is what we call refracting. We'll see later on an application of the bending of the light due to the motion from one medium to another is lenses. That's what makes lenses work. Let's explore that with a simulation. Okay. So here in this particular case, we have a beam of light shown from a laser, and it's going to meet the interface here. You see it here, light, color, that's one medium, a little darker shade, it's the second medium. And we have here the perpendicular to the medium where the light beam meets the interface. And we have a graphic here of the reflected part of the beam and the transmitted part of the beam. Remember, when we talked about incidence, we measure the angle of incidence relative to the perpendicular. That's my angle of incidence. And the angle of reflection is going to be equal to that, again measured relative to the perpendicular. That's my angle of reflection. Now, the angle of transmission is going to be measured relative to the perpendicular again. And this is the angle of transmission. And you notice that the beam is bent, it's not moving straight. Now, for this particular simulation, we can show a few things. Okay, you see this red line here is showing us how the wave of the light beam is oscillating. Now, the simulation is breaking the wave in two types: the part that's oscillating like this, and the part that's oscillating perpendicular to it, that's perpendicular to this, which is going to be in and out of the screen. Now, it is showing us in here the actual intensity of the light that is reflected for each part of the wave. And we can make it show us the real intensity of the waves. Now, for what's called the P wave, which is oscillating in this direction, the reflected intensity is 6.2%. while the reflected intensity of the S wave is 24%. And when we look at it, you see it is darker here. So as you notice in this particular case, what we do see is that most of the light is transmitted, not reflected. Now, how much of the light is transmitted and reflected is going to depend on the angle. We're not going to get into figuring out the intensities in this particular course. We are going to deal just with reflected and refracted light. Now, but as you notice, as I change the angle, the intensity of the reflected beam changes. The intensity of the transmitted beam also changes, but you don't see the change as much. And this is for the S wave. For the P wave, we are going to see a similar thing. Okay, you almost see nothing here, and it is stronger then. Now, notice that the beam, instead of moving in a straight line, it is bending. Now, I'm going to move my laser beam here to the middle so we can see more stuff. And then I'm going to make it hit the surface at a perpendicular angle. So my angle of incidence is 0. Notice that in this particular case, we don't have any bending of the light beam. When the angle of incidence is 0, the angle of transmission or refraction is 0 as well. Okay, so that's the case when it does not bend. However, for all other angles, it's going to bend. It does not move on a straight line. Okay. Now, the question might be, why does it bend? One of the best explanations, Fermat came up with it a few centuries back, which is the fact that light is going to take the path of the shortest time to get from one point to another. In other words, whatever path is going to take light to get it to arrive to a point faster is the path that the light is going to follow. Now let me try to explain what does that mean. To explain that, I'm going to first show you this particular simulation. You notice here we are representing light as a wave, not just as a ray like we had it in the previous simulation. And okay, the ray representation, we have it here. You see, that's an arrow pointing to the way the light beam is traveling. But light is actually a wave that travels in all directions, and we are showing here the front of the wave as it is traveling. And you see crest and troughs, and then they meet the interface. So they're going to meet the interface at all points. Now, notice what happens as it moves to the other medium. We have a different wavelength. Why do we have a different wavelength? Because the wave is traveling slower in the second medium. Remember, in this particular case, it is slower. Now, if I make both media identical by having N1 equal to N2, and I'll talk about N1 and N2 in a little bit, you notice that there is no change in wavelength. If I make N2 larger, let's say by putting it 2, the reverse will happen. If I make N1 larger, instead of N2, so we can see the reverse happening. Short wavelength changes into a large wavelength. Now, so the point I'm trying to get across from here, the most important point is the wave is not traveling just along a line. It's traveling in all directions. So when you think of light, you should not think of it as taking just that particular line along which it's going to travel. Another thing I would like to show you here before we go on, so far here I'm showing you only the incident wave. I'm going to show you the reflected wave here, and you see it's a much lesser intensity. I can change the intensity of both reflected and incident here by acting on the amplitude. I just did that. But this is our reflected wave. So in actuality, in the first medium, what are we going to have? At any point in space, we are going to have both the reflected and the transmitted wave. So actually, it's going to look like this. An interference of both of them. Both of them are going to happen at the same place and are going to add up at the same place. interfering and giving us something that looks somewhat like this. So it's kind of a more interesting, complex world. If we look just at the incident, that's the incident. Just at the reflected, that's the reflected. But the real world has both. Okay? Now that we have that point, the fact that the wave does not travel in a straight line, let's look at it some other way here. What I'm going to do is draw one medium, medium 1, and medium 2. And this is the interface between them. And I'm going to have light originating at this point, and I would like it to get to this point. The shortest, the straight line path from point 1, okay, or point P1 to point P2, the straight line path would be a straight line from here to here. That straight line involves two distances. One distance that's traveled in medium 1, let's call it D1, and one distance that is traveled in medium 2, let's call that D2. Remember that light travels faster in D1 than in D2. Now, to take the shortest time to go from P1 to P2, remember again that light, I'm going to draw it in yellow here, is not traveling as a ray, and actually it's going to be a wave that's going in all directions. Now, to get the shortest time to get from P1 to P2, we need to maximize the time we travel at distance D1, at medium 1, and minimize the distance traveled in medium P2. Think of it this way. In trying to go from one point to another, you can take the freeway, where you can travel fast, and for part of the way you can take the freeway, and part of the way you have to take side roads. Now, to minimize the time it's going to take you from point 1 to point 2, you are going to try to maximize the amount of time you are going to spend on the freeway, because there you are traveling faster. And that's what we are talking about here. To get from P1 to P2, the freeway is being in medium 1 here, if we are moving faster in medium 1. So we need to try to maximize D1 and minimize D2. And how do you do that? One option might look like increasing D1 as much as we can and decreasing D2. And that's the path that the light is going to take. And you see in this particular path, there is a bending. Let me show you that with a simulation. Okay. Now in this particular simulation, oops. So what do we have here? We have one light beam. This is the origination. This is point P1, and this is point P2. And this is the time in this graph that it's taken the beam to go from P1 to P2. We can move the point where the light is going to hit the interface. And you notice here, as we move it, we can see the time. And in this particular case, you see the minimum time is when we have the light move a straight distance without bending. Okay, now that's for normal incidence, when our angle of incidence is 0. what about if this is where my P2 is? And let's try to figure out the point. Okay. See here, you notice the point where it's going to take the minimum amount of time happens here. That's when the light is going to bend. Okay. So this is the idea behind what causes light to bend when it moves from one medium to another. Of course, I could have showed you with a simulation how you can see the reverse if you are moving from a high N to a low N, so you minimize then the top and increase the bottom. Okay, so a few more things here in talking about light refraction. One of the symbols that you have seen in the simulations I have used and in the text that we have seen of the previous slides is what we call the index of refraction. Okay, to get the index of refraction, let's have a reminder. Speed of light in vacuum is 180,000 miles per second. In meters per second, it's about 310 to the 8 meters per second. That's the speed of light in vacuum. What we know so far is in all other media, the speed of light is going to be smaller than that speed of light in vacuum. And that speed of light in vacuum, we give it a special symbol that we call c. Okay, we have it here marked. So whenever light travels in a medium other than vacuum, it's going to travel with a speed that is less than c. Now, for example, in air, it's going to travel less than c, but it's not going to be much of a difference. But in water and glass, it's going to be quite different. The speed of light in any medium is given by this expression. V is equal to c, the speed of light in vacuum, over n. That's the way we define the index of refraction of that medium. So it is a measure of how much that medium is going to slow down light. Because light is going to travel slower than c in any medium, that means n, the index of refraction, under normal circumstances, is going to be always larger than 1. We'll see later on that the index of refraction can depend on the wavelength of the light. It's a slight dependence, but it's a real dependence. And that causes what we call the dispersion of light. But let's not get into that this minute. Okay, now, I had this expression in the first slide. Now, one nice thing about when light refracts from one medium to another, the law that governs how it behaves, it's a very simple expression. N1 sine of theta 1 is equal to N2 sine of theta 2. Let's explain what these symbols mean. So if I'm in medium 1 and light is going to medium 2, we draw the perpendicular to the interface. So if I have a light beam coming in and making an angle of incidence theta 1 relative to the perpendicular to the interface, if medium 1 has an index of refraction N1 and medium 2 has an index of refraction N2, then light, instead of moving in a straight line, is going to bend, is going to refract and travel in the second medium at an angle of theta sub 2 relative to the perpendicular again to the interface. The relationship between theta 1 and theta 2 is Snell's law. N1 sine of theta 1 is equal to N2 sine of theta 2. Notice in this equation, if N1 is larger than N2, then that makes theta 1 smaller than theta 2, and the reverse. if n1 is smaller than n2, then theta 1 is larger than theta 2. That's what we have in the figure here. Okay, just applying that just as a quick reminder. So we have both media, theta 1 and theta 2. I mean n1 and n2, and the light beam is moving in with an angle of theta 1 to an angle of theta 2. And we see that theta 2 is larger. From what we just mentioned, n1 sine of theta 1 is equal to n2 sine of theta 2. Now, if the indices were the same, then theta 1 would be equal to theta 2, and we have no bending. So that's not an answer. Now here, what we have is theta 2 larger than theta 1. That means n2 is smaller than n1, and that's our answer. Answer 1. Okay. Remember from the simulation I showed you earlier, usually there is both reflection and refraction, but at different intensities. Let's take this example. In this particular example, what they do is they're giving us the indices of refraction. They say light is going to move from air, where the index of refraction is 1, into water, where the index of refraction is 1.33. And they say that the beam is reflected at an angle of theta sub r equals 60 degrees. So they give us actually this angle. And they are asking us, what is the refraction angle theta sub 2? Now, here they are playing a little tricky, not much really, but instead of giving us the angle of incidence, they are giving us the angle of reflection. But we can easily remember that angle of reflection is always equal to the angle of incidence. So my angle of incidence is just 60 degrees in this case. So we know the angle of incidence, so we can apply that to Snell's law. In this particular case, that's going to be 1 sine of 60 degrees is equal to 1.33 and 2 sine of theta sub 2. So solving for theta sub 2, I solve first for sine of theta 2, and that's going to give me 1 sine of 60, that's sine of 60 over 1.33, and then I do sine minus 1 of theta 2. If I have my calculator in degree mode, I made a mistake here. Let me erase this. So theta sub 2 is sine minus 1 of sine of 60 over 1.33. Okay, and then if you have your calculator set in degrees, you should find this at 40.6 degrees. Okay, so that's our example. One implication of Snell's law, whenever you have an object that's partly in one medium and partly in another medium, like these pencils, because light, as it is coming out of this one medium into the other medium, because of that refraction, is going to give us the illusion that our objects, like these pencils here, are actually bent. It is actually the light that bends, not the objects, but that's the way it looks. That's one implication of Snell's law. Is going to result in images being distorted. Notice here also it looks thicker in the water. You know, depending on the way you look at it, it looks thinner here.